Good afternoon, everyone. Welcome to the colloquium. Today's speaker is Ali Mashayek, who comes to us from Cambridge University, where he's professor in the Department of Earth Science, but also very closely connected to the Department of Applied Math and Theoretical Physics. It's a real pleasure for me to introduce him to you today, especially because he completed his doctoral degree here in our department just 11 years ago in our group. After finishing his doctoral degree, he moved to MIT with an NSERC postdoc, and he worked there for about 3 years, 2.5 years in Raphael. Yes, that group.
Ferrari.
Yeah. So he was about 2.5 or 3 years at MIT in Ferrari's group, which was a very high-powered car-like operation. And the work he did there was in the context of the DIMES project, which was basically studying mixing in the Southern Ocean. After finishing his postdoc with RAF, he moved to the Scripps Institution of Oceanography, where he spent the better part of a year working with Matthew Alford, who's also been a speaker in this colloquium. So after the work with Alford, he began looking for a permanent position and eventually accepted one at Oxford University, which was a Royal Society position. He stayed at Oxford for about 2 years and then traded that position up for a faculty position at Imperial College London, where he again stayed for about 2 or 3 years until moving to his present position in Cambridge University. His trajectory since completing his doctorate degree here has been one of extremely rapid rise. Today, he has a very large group working on ocean turbulence and the mathematics of the climate system at Cambridge University. So it is, again, a great pleasure for me to welcome him back to Toronto. And please help me in welcoming him to this colloquium.
Thank you, Dick. Very, very nice to be back. And I'll wait till the end of the talk and I'll thank the department properly. But in terms of career advice for young students, what Dick said, don't do that. Do a good PhD, do a postdoc, get a job, get a life. So there is a flip side to that. So what I'm going to say, is there any chance we can have this one off? So what I'll talk about today is about the role of the ocean in the climate system. And as the title says, it's about the long-term history in this system. And as a warning, at the end of the talk, there won't be a punchline. I'll try to show you from a mechanistic perspective what the timescales are and how they interconnect, but there won't necessarily be a punchline in that. What do we do with that? But along the way, hopefully, I'll actually try to show why that's important operationally. But the talk in general is a summary of my journey from a student here doing turbulence to trying to learn about components of the climate system, and all of this happening in a decade where climate mitigation adaptation actually has increasingly become an active part of climate scientists' life if they choose to. And so there is an urgency in action and creating methodologies and interventions while the scientific knowledge can't evolve on that timescale and you really can't force it. So I'll touch on that sort of towards the end. So this video was meant to show you that ocean circulation is complicated and it is sort of full depth. So with that, so very basics, why do we care about the ocean circulation? Well, the main two reasons we can mention, the heat budget and the carbon budget. If you think about the heat budget, we know that most of the carbon in most of the heat in the system, anthropogenic heat, is going into the ocean, 91% of that. And if you actually, maybe I can use the stick. So most of it goes here into the ocean. And if you break that down, a lot of it actually go to the deep ocean, below 100 meters to thousands of meters. And if we look at the meridional heat transport, as we know, ocean and atmosphere basically take the equatorial heat and send it poleward, and that's sort of critical to the heat distribution on the planet. And it's really important for how life evolved on the planet. So that's the contribution of the ocean. That's the atmosphere. Atmosphere does most of it. If you break down the ocean into the different basins, it's more complicated. So it actually is really important for distribution of heat on the planet. You put that together with that, that basically makes the point that the video that I showed is important. We need to understand how the ocean circulates and how it interacts with the atmosphere to get that heat and store it in the ocean, and what are the timescales of that. So that's basically the heat. And if you think about the carbon, that is showing the air-sea exchange of carbon. And you can readily see the importance of the atmospheric dynamics. And you can pair that visually in your mind with the ocean dynamics, ocean circulation video. And so there's an oceanic component to that of carbon uptake. And if you think about reservoirs of carbon in the system, just as a reminder, we have about that many gigatons of carbon in the atmosphere, which is more or less about what we have in the surface water. And if you look at the reservoirs in the water, like just the organic carbon in the ocean in terms of gigatons is comparable. That's relevant if you think about marine CDR by tweaking the ocean biology, right? That's the one you're actually interacting with. And when you go to intermediate to deep ocean, it's 2 orders of magnitude more, right? So if you think about climate interventions, and for the record, I'm not a pro-engineering person, but it is something that everybody is looking at. If you think about that, the carbon in the ocean is actually integral to life in the ocean. So from an ecosystem perspective, you have dissolved carbon in the upper ocean that gets built into shells of phytoplanktons as they use nutrients and sun to build their shells. And then some of it dies and goes back, it sinks to the deep ocean, and that's the carbon pump. That's how you get carbon from the atmosphere to the deep ocean. It dissolves along the way, a part of it gets to the sediment, and that's a longer term sort of taking out of the carbon out of the system. And then the rest of it is actually going through the food cycle. So the phytoplankton, the zooplankton is the phytoplankton and fish and so forth. And as I mean, if you zoom in, from a physicist's perspective, I find biology quite annoying. And so when my students start talking about 10 different types of phytoplanktons, I just don't know what to do. So I just say that I don't discriminate, and to me they're big or small, and that's it. So, but I'll come back to that. But all of those actually really matter. So, a very quick few-minute overview of ocean circulation. I'll start from this video from NASA. So this is a high-resolution modeling that's constrained by data. There's quite a bit of remote sensing. There's some constraint from in situ hydrographic informations and so forth. This is showing the temperature. So you can see the range of scales that help transport, for example, heat from the equatorial regions to the polar regions. And you have the gyre circulations. You have the western boundary currents that are really key to polar transport of heat. You have the Antarctic circumpolar currents that are really key in isolating the Antarctic climate. I'll talk about that a little bit. But if you think about the scales of the problem, spatial scales, you're thinking 10,000 kilometers. And now you're talking about mesoscale eddies that are, tens to hundreds of kilometers wide. And then you go to sub-mesoscale dynamics that are smaller, all the way to turbulence that goes to sub-centimetre dissipation, where the energy is taken out of the system. So, and all of those scales actually are important and matter. So it's a very difficult multi-scale problem. But for the rest of the talk, what I'll do is to oversimplify this and just show you arrows. So if you average that in time sufficiently, this is an overly simplified view of the ocean circulation. If anybody here is from New Zealand, I apologize. It is not here, but that's usually the way to identify them by just showing this. But if you go around this, at polar regions, we form deep waters because it's cold and you form sea ice. And when the sea ice forms, the salt is rejected, brine rejected. So you end up with salty cold water that's very dense, and it sinks to the deep ocean. And it happens in the North Atlantic, in the Weddell Sea, in the Ross Sea. And it's very important to notice that all of the deep ocean is filled with waters formed at these very few locations in polar regions, right? So they're really important. We know that polar oceans are really important, but they're really important, and they are where the deep ocean exchanges information with the atmosphere. So when you have short circuiting of information. Now, water sink here, a combination of rotational, inertial, frictional forces create dynamics that lead to it coming south. Winds in the Southern Ocean can pull waters up, a process called Ekman transport. And then through the Southern Ocean, the waters can actually exchange between different basins. So the opening of the gateways in the Southern Ocean is really key, right? In the present day ocean, if one of the basins gets denser for whatever reason, they can adjust through the opening of the Southern Ocean. But that's not always the case as we go in the back. So one of the examples, I'll talk about the opening of the gateways and shaping the present climate. So I'll come back to that point. But waters go to different basins. Turbulent mixing, small-scale turbulent mixing brings the dense waters up in the water column in the same way that you stir heavy cream, heavy cold cream. If you just pour it slowly to the bottom of a cup of hot coffee, you have to stir it for it to come up. So tides and interaction of ocean dynamics, eddies and currents with rough topography creates that stirring and brings the dense waters up. Those would be these arrows. And through different passages, the waters find their way back up to there. And the time scale of this is 5 to 10,000 years. So the oldest waters that are well in the North Pacific could be really 8,000 years old. And that's a very good measure of the memory in the system, in actually age of water that we can work with. Now we can further simplify this, and if you, in your mind, zonally average that, you get this double gyre circulation that we usually show when we talk about the ocean meridional overturning circulation. So if you see MOC or MOC, that's what it refers to. If I showed in the Atlantic, it would be AMOC, Atlantic, MOC. I try not to say that, but if you see it, that's what it means. And this is showing oxygen, so you can actually see when it's purple, it means it's water that's been in touch with the atmosphere more recently. So that's younger water sinking, again, the North Atlantic. And this is really old waters that are in the Pacific Ocean and are bubbling. And if you think about energetics of this, there's winds in and out. Wind at the surface helps drive the ocean dynamics. And then you have precipitation and evaporation, basically buoyancy forcing at the surface. And inside you have mechanical forcings by tides and flow topography interactions. And there's a little bit of geothermal heat flux from the crust that one could argue could be important or not. Overall, that's basically the energetics of driving this. Now, for context, it's important to remember that this is about 10,000 kilometers, and this is 6 kilometers, right? So you're really thinking about something that's just like a piece of paper. It's really thin. And that's what that means energetically. It means that the energetic of the horizontal motion along density levels of the MOC is about 1,000 times larger than the energetics that is needed for this stirring and mixing to bring waters up. And that makes it a challenge from a climate modeling perspective, because you construct a model that can resolve and simulate the large-scale dynamics of the system. And this is really important, but its energetic is within the errors of the energetics of the larger scale flow. Again, that becomes relevant a bit later in the talk. Okay, now I'm going to talk about the scales in the system. And I thought it would be nice to start from this paper by Curries and Hoybers that it's from about 10 years ago or 15 years ago. And here they're showing some measure of energy in the system. You can think of it as surface temperatures. And that's zonally averaged. And this is the spectral decomposition of that. And you can see the annual cycle and other seasonal cycles, and we do understand them. But the key is this one. This is the autobicoherence of the signal. And when it's above 0.1 is significant. And when it's blue, it's really significant. And this is showing that scales of annual cycle are all the way statistically significantly correlated with timescales of 100 years. right? So if you actually care about dynamics in the system on annual cycle, it actually can feel the past 100 years, right? So that's quite important. And you can show that another way. You can look at temperature records and the spectral decomposition, and you would get what we refer to as a continuum. Now, these are all paleo proxies, and I don't know most of them. But if we think about two of them, they're all paleo proxies that are some measure of temperature or energy in the system. But if we take two of them, we can think of the oxygen. This is the isotopic ratio of oxygen, oxygen 18 to 16. And this is from ice core from Greenland. And that is a measure of the temperature of the ice when it was formed. And you can actually trace it back hundreds of thousands of years. And this is the same isotopic ratio built into the shells of phytoplanktons and microorganisms that is now stored in the sediments. And from that, you can work out the temperature of the water when they built their shell. So these are measures of temperature, the polar region, the deep ocean, sedimentary, going back in time. And when you look at the spectral decomposition of that, you see a continuum. And we know when we see a continuum like this, it implies that there are nonlinear interactions in the system between the scales. And this is 100,000 years all the way to annual cycle. And there are many signals here that are very well understood. This line is the Milankovitch cycle, the 40,000, 41,000 kiloyears. This is the annual, and this is halfway between that. And you can, when you do these type of calculations, you can see breaking in the slopes at places that sort of make sense. This is centennial, annual, and so forth. And this is basically a separation point between dynamics of the upper ocean, and then you start interacting with the deep ocean. And this is quite well known in dynamics. When you study turbulence in different regimes, you actually get different slopes. So from that, you can work out what sort of nonlinear dynamics could be relevant in the system. Now, we're going to look at the same spectral decomposition over a much longer time scale. But to do that, we're going to look at a much longer record now, going back over the whole Cenozoic period of 65 million years. So this is oxygen isotope ratio from benthic foraminiferous shells. So they're sedimentary records. And from that, you can work out the temperature of the ocean when they were built. There is a correction due to ice volume at in the polar regions, but that aside, that's a measure of temperature. Now, I'm showing this to make the point that there's continuity in the record, of course, but that it actually does matter. I mean, one example is that we can actually look at this transition point. We can actually think about the Eocene climate. It's quite popular to study because it was a hothouse climate, and the atmospheric CO2 level at the time were basically around the worst case scenarios that we think we might be going to. So it's useful to study that to see if we are going to go into a climate where this is going to be Antarctica, which is what it was during the Eocene. Now, if we look at the geometry of the ocean circulation at the time, this is the Arctic and that's the Antarctic. And you notice that the Drake Passage was closed. And as a result of that, you had a subpolar gyre here that was bringing heat to Antarctica, and you did not have an Antarctic circumpolar current that would isolate Antarctica. Right, so if we start from here and pay attention to this gray line, that's the Antarctic ice sheets. And around here, they start growing. And I mean, this is not as certain as this plot suggests, but around this time starts growing. And among other reasons, from an oceanographic perspective, what happened was that as the gateways opened, the subpolar gyre that was taking heat to Antarctica disappeared, the ACC grew and isolated Antarctica, and one starts forming deep waters around Antarctica, you get freezing, and the climate here changes. And in the Arctic also, the geometry changed in a way that you started getting freezing and deep water formation. And I will not discuss that today, but one thing that we're studying in my group is the fact that in present-day ocean, the deep ocean is sufficiently stratified that the tides can scatter into higher mode internal tides and create mixing. And that mixing is really key to bringing the waters up and having a circulation. But if you go back all the way to here, the deep ocean was likely not as stratified as today. And so it could be that there was not as much mixing and mixing-driven deep ocean circulation. So from a deep ocean sort of geophysical fluid dynamics theoretical perspective, there are reasons to believe that something actually really changed in the way that the ocean circulation operated before and after that transition. And this also was a marine extinction event. The Eocene, Oligocene period was a marine extinction. Now, all of this to say is that the climate at this carbon dioxide levels of the Eocene probably looks very different than if you actually go there, because not only the geometry of the system was different, and that is the geologic history, but also the dynamical redistribution of heat on the planet by the ocean was quite likely very different. And also the redistribution of nutrients in the ocean, the mechanisms of ocean circulation was different. So potentially for the same CO2 levels, you would have a very different biodiversity and ecosystems in the ocean. Fun fact, this is the PETM, the Paleocene-Eocene thermal maximum. This is a carbon isotope ratio that is a measure of primary productivity in the ocean. And also it's a very good measure for methane. So we know that at PETM, about 1,500 gigatons of carbon were released into the atmosphere over 2,000 years. We have already done about 400 gigatons over 250 years. So much, at least a factor of 2 faster. And this is an episode which we know for a fact that it was complete, near complete shutdown of marine life. And I find that quite scary when we think about ocean biodiversity. Now, the record that I showed, this one, we could do the similar decomposition as Curry and Hoiber's, and you get a continuum. And even though it doesn't look like, if you put the two together, the slopes actually line up quite nicely. And when you do that, you actually find something that I think is interesting. So this is the oxygen isotope, you can think of it as temperature record of the system, going all the way back to a few hundred millions of years. These two are reconstruction of atmospheric CO2 from 2 different reconstructions. One is just based on marine records. One also has terrestrial information in terms of proxies. And this is the thermal heat flux from the Earth's crust into the ocean, built around based on tectonic motions that are constrained by paleomagnetic data. It's very interesting that these slopes actually line up quite the same. And if you think about the scales, this tends to a few hundred millions of years. You're thinking about tectonic motions. When you get to here, you're now about a few millions of years. Now you're getting to the scale when the evolution of ice sheets timescale lines up with the evolution of mantle convection. Not mantle convection, sorry, the tectonics. So the geometry of the ocean and the ice sort of converge in terms of timescales in a few million years. And that's where you get a break in the slope of the system. But importantly, I think this represents the continuum related to the dynamics of the interior of the planet, whereas that is relevant to the climate dynamics of the cryosphere. And then as you go that way, you get to the ocean, ice sheets, ocean, and the atmosphere. So typically when we think about the memory in the system, we think about the interior dynamics as a source of outgassing that can change the climate immediately. When tectonics motions can create outgassing in the sea and or on land, and that can create outgassing and change the climate. But what I'm suggesting is that there are other ways through the geometric constraints of the ocean circulation that you can actually have a more direct interaction between the scales going forward. So point being that from 100 million years all the way to when the energy is dissipated in the system, we have a continuum of information. Now, to give you a more sensible example, which is more relevant to present day, I mean, I'm in an earth sciences department, so this would be considered modern, right? So if you think about modern climate, these are 2 temperature records, one from grip. This is from Greenland, an ice core from Greenland, and this is an ice core from Antarctica. And just measures of reconstructions of paleo temperatures. And I mean, there are many variations, and mechanistically, why you had oscillations between stadial, interstadial is a complex problem. This group here has worked on that quite a bit. Just want to show this schematic from a paper by Guido that was here working with Dick for a long time. I imagine some of you know. And this shows an asynchronous warming and cooling of the two poles, which is usually referred to as the bipolar seesaw. And the idea is that the ocean has, you can think of the ocean from a dynamical system perspective as having a slow manifold, which would be the circulation of the deep ocean, and a faster manifold, which is the, shallower upper circulation in the ocean. And those are the two ways that the polar oceans interact. And the ocean has a very large heat capacity. So imagine when you slow down a circulation in the Atlantic Ocean, the upper Atlantic Ocean, what that implies is that you won't transfer as much heat from the equator to the pole. You start cooling the Arctic Ocean. That leads to more deep water formation. It takes longer, but that can actually get to Antarctica and impact that. So the heat capacity of the water and the two different speeds of operation provides a dynamical system in which the ocean basically acts as a buffer. So when you heat up one pole, the other one is cooling off, and that leads to the circulation passing that information. And when the other one is cooling off, that leads to the first one warming. And this has gone on in the past couple of few million years. That has been a feature of the system. So we know that the system didn't always operate that way. Relatively speaking, is modern. But if we get these two temperatures and plot it like a phase space plot, you actually start getting loops. This is the actual data. This is basically that mimicked in a couple climate models. But if you just focus on the data, you start getting loops. And what that means, anytime you see two lines colliding, it means that for the same conditions, you can have a different climate, right? And this implies that the path that you get to a certain climate is key. And this is very well known in climate dynamics. But that actually gives rise to a question that's quite a hot question now, a lot of people are working on, which is, are we heating up the planet so rapidly that both poles are really heating up at the same time? So we're going out of this bipolar seesaw. Now that's an open question. I don't think we still know the answer to that, but I can show you an example of how people have been thinking about it. So this is from a paper that is, again, somewhat old, but there are newer versions saying the same. But this is showing the surface temperature trends. This is from Goddard Institute, and from 1979 to 2005. And this is very well known that the warming signal is much stronger in the northern hemisphere. There's more land and atmospheric dynamics and so forth, but ocean also plays a role in that. Now, if you remember the ocean circulation, the two-cell pattern, we know that there is a source of heat in the North Atlantic. You can think of it as the anthropogenic signal, the anthropogenic heat. And it takes anyway from some decades to 100, 200 years for that signal to get to the Southern Ocean through the circulation, right? And so you start warming the system, and that heat 200 years later gets to Antarctica and has to go through the ACC system, through the current to start melting the ice shelves. And up until a few decades ago, the Antarctic ice sheet as a whole was still gaining mass, right? But it seems that in recent decades, East Antarctic, West Antarctic, when you add them up, is also losing mass as a whole, similar to Greenland that has been losing mass for a while. And now this is observations, but one can ask the question, is there something about the ocean circulation that's actually causing that? There is. If you look at the models, it's very well established in CMIP models that the upper branch of circulation has a chance of slowing down. And we've heard about that quite a lot. The Gulf Stream can shut down and so forth. But what is new? This paper came out last year and made quite a buzz. This is from a high resolution model and suggests that the lower branch of the circulation might also be collapsing. And again, the bipolar seesaw that I explained would not necessarily support that they could happen at the same time. Now, we try to look at that using data. So this is work that's led by my student, Josh, in collaboration with Matt Maslow and Sarah Perkey at Scripps Institution of Oceanography. Alberto Navarro-Garabot at the University of Southampton, and Martin Seegert at the University of Exeter. And we use data from ship-based measurements of ocean properties. This is a GLODAP program. These sections are sampled, and you go to sea in harsh conditions for months, and you keep sampling. So a lot of efforts, human labor, and also very expensive international programs. And then we have a more smarter way of doing it, which is thousands of floats that go up and down, measure stuff, and then transmit the signal, and that's the Argo program. And together, we can actually look at the heat that gets to the Southern Ocean. So a very quick overview of the ACC dynamics in depth. Like I said, the Southern Ocean is open. As a result of that, you can spin up jets going around the system, like the jet stream. Now we know, and this is the jet, and it's vertically sheared. So the horizontal velocity decreases as you go down. And that in thermal wind balance is balanced by the meridional density gradients. And that's why you see the density levels sloping. And that's really key because these density levels connect the atmosphere to the deep ocean. Southern Ocean is a net significant sink of carbon along these density levels. And all of that exists because of this geophysical fluid dynamical balance that exists because of the opening of the Great Passage and the geometry of the system. Now, in terms of waters, these are what we refer to as the circumpolar deep waters. You can think of it as waters that come from the North Atlantic, and they have basically the warm waters that are important in that they can melt the ice shelves. And around the shelves, you form shelf waters because it's cold and salty, as I said, and those waters can actually sink and form the Antarctic bottom waters. And there is a competition between the two. If you have more shelf water, you can keep the circumpolar deep waters away and so forth. So if we look at that data, we can now actually see a trend. Over the past 20 years, we can see an expansion of circumpolar deep waters shown in red around Antarctica. And we can see a diminishing of Antarctic bottom waters in blue as a negative sign around Antarctica. So that is sort of, I would say, a first definitive observational evidence that one is collapsing and the other one is expanding. Now, that's just 20 years. It could very well be just natural variability. If we do a principal component or EOF analysis, break it down into its components, most of the variance is in a trend. Then you can look at second, third, and other modes, and then those do correlate with modes of variability in the system, southern annual mode, Pacific decadal oscillations, and so forth. But there seems to be a robust trend in which the heat is encroaching Antarctica, and that the deeper branch of circulation is diminishing. Now we can look at that even further. So we assimilate the data in a high resolution model, and we produce a result that can resolve the dynamics all the way to the ice sheets. And then we built into the model a reconstruction of the ice sheets, the best that we can get our hands on, and we produce a numerical solution based on the data assimilation. And then what we did is that we used the SEAL data that thankfully sampled a lot of information at depths in regions that are very difficult to sample, in cold shelf regions. And they actually do a lot of that during the mating season. So with that, we can verify the model output in the shelf regions is reasonable, is comparable with the observation. So we can actually trust the model in that it's not complete nonsense. And this is just to give you a sense of the resolution of the model. So that would be an ice sheet, and that would be the bedrock, and that would basically be a cavity. And the question is the heat that's coming, let's say, from the Atlantic, how can it get into the cavities, and how can it actually destabilize the sheets to the point that they can collapse? So this is the circumpolar deep water, which is the source of the heat. And this is the water that's forming on the shelves, the shelf water. And if you compare them, you can see where one is strong, the other one is weak, and you can go around and see the anti-correlation visually. And then you can actually look at it a bit more carefully. For example, in a place like the Weddell Sea or the Ross Sea, when you have sort of very robust formation of dense waters that feed the Antarctic bottom waters, the shelf water is strong and is sort of holding back the heat that's coming with the circumpolar deep waters. But if you look at here, you actually notice that there's seasonality to deep water formation. It doesn't happen all seasons. When it forms, it keeps the heat away, but when it doesn't, the heat can make it up to the ice sheets. And then you can look at another region, and here the seasonality comes from the winds. The wind seasonally could bring more waters up and give you a higher melt rate, or it actually could do the opposite or do nothing. So there is a variation around Antarctica when you think about the stability of the ice sheets from a heat transport perspective. And if I put it all back together to go back to the scales, the geometry of the system is set by processes that operate on tens to millions of years. Then the dynamics, the ice sheet, the formation of that, and the geometry of the ice sheet, the loading, its configuration with respect to the bedrock, which is really key to stability. All of that is set on millions of years to hundreds of thousands and shorter timescales. Then the equilibration timescale of the ACC and the ocean circulation, you're talking about 10,000 years and smaller. And then you get to seasonality of winds and interannual variability of the winds that can help bring the waters to the shelf. And then you get turbulence that goes all the way to seconds. So you can actually see the full continuum that lead to the ice melt due to circumpolar deep water encroaching upon Antarctica. So that was a sort of dynamical perspective of how they all interact. You can make it a bit more complicated, and you can put in biochemistry. Now we basically stumbled upon a result that we didn't expect. We were tweaking the turbulent mixing in a data assimilation product. So this is a data assimilation product. Here we're plotting the erosive flux of carbon. So around Antarctica, you form deep waters, you get green. Carbon is going to the system. These are waters that just upwell in the Southern Ocean and start going north. So they are actually outcasting carbon to the atmosphere. And then they get cold again, they lose their heat, they sink, and they take more carbon back into the system. But if you integrate this zonally, and also from Antarctica north, you get a net sink. So by the time you get to 30 south, it's a net sink. Now, what we did is that we changed the background vertical mixing in the model very slightly. So over Antarctica, I mean, it's a very windy place. You have storm tracks. They create a lot of turbulent mixing. There's a lot of mixed layer dynamics, mesoscale, submesoscale activity. So those are parameterized in the model, and they give you a very large diffusivity of 10 to the minus 2, 10 to the minus 3. What we tweaked is much smaller the background diffusivity that is in the model that could come from topographically generated waves that make it all to the surface, or waves that are generated further north in the basins, like internal tides and shoal in Antarctica. And there's some mixing under the sea ice that we don't still fully understand, we haven't parameterized. So it's a background, very weak turbulence. We changed that over a very conservative range. And what we found was that over a year, that changed the net sink of carbon over the Southern Ocean by up to 100%. So it's a perturbation, and we let it go to 6 years, and you still have 60%. So I find that quite scary, that a system is so hypersensitive to a parameter when we actually change it over a range, that a physical oceanographer would say that's not much. I don't really care. Go with whichever number. And to actually explain a little bit more why that happens, like, for example, this is the same two perturbations. If you look at the Argentine basin and around here, it's a region of upwelling. Turbulence generates a current that can bring nutrients up to the surface. So that slight shift that we do to the mixing actually changes the distribution of tracers. Here I'm showing you iron. The reason I'm showing iron is that the primary productivity in the Southern Ocean is significantly iron limited. So you change it a little bit, it actually makes a massive difference. So you change that. This is the surface that's 125 meters deep. You actually change the distribution of iron in the surface and deeper. So point being that the dynamics evolve on a longer time scale and equilibrate. If you have a passive tracer on that, you can mix it on a much shorter time scale. If your passive tracer is a nutrient, that is the limiting factor, then you get this hypersensitivity to very little changes to mixing. It can actually very significantly impact the system. And the way it actually effectively changes the system is that perturbation changes the partial pressure of the dissolved carbon dioxide in the seawater. And we can understand why. We can break it down into changes due to temperature, dissolved inorganic carbon, and alkalinity of seawater. And all of this is still carbonate chemistry. You're just moving tracers around. There's no biology. And I'm not going to talk about it today, but we've looked at the biology side of this, the productivity, and it actually does change the carbon export into the deep ocean as well. And finally, I'm not going to talk too much about it because I don't fully understand, but this is work that, actually, I forgot to say, this was work that my former student, Lizzie Ellison, did with Matt Maslow at Scripps and Lara in Cambridge, who gave a talk here a few weeks ago. And this is work that my student Sophie is doing with Colleen Petrick at Scripps Institute of Oceanography and Kale, who is at the University of Chicago. So we've added ecosystems to what I showed you before. Now we have zooplankton that eat the phytoplankton and the fish. And in the process of constructing that, we actually found the system is really sensitive to the appetite of zooplankton. And the reason we did this because we have a funding to look at the hazards of iron fertilization. So we wanted to know what happens if you fertilize the ocean, what is the impact on ecosystems. And one of the things we found in the process is that we can actually constrain the grazing rate of zooplankton and phytoplanktons. And when you actually change that quite a bit, you can change the marine chemistry, biochemistry quite significantly to the point that it can feed back on the carbon cycle to leading order on annual timescales. So it gets increasingly complicated. And I'm increasingly working on things that I know less and less about. So this is work that my student Heiming is doing with my colleague Ramit in Cambridge. And so we've started looking at very simple, low complexity socioeconomic models. And they typically have a climate component, that's the climate model component. They have sort of an economy component, and then they have a carbon component. That's where your interventions could come into play. And you can ask interesting questions. You can ask questions like, what if we could fertilize to the point that it would scale up and actually take carbon out of the system, but it would damage the ecosystems in a certain way? And then you have to do a valuation of the ecosystems to the point that you can put it in a socioeconomic models. That valuation doesn't exist. So blue economy, for example, is a concept, is not practical, but you can actually do this type of modeling to provide a comparison between the benefits of a solution and the disadvantages of that in economic terms, theoretically, because you get the ratio of benefit to damage to a biomass of value X. And that sort of conceptually gives the tool to the economists to actually make an argument that there is a blue economy that we can build. And this is done through funding coming from UN Sustainable Development Goals. And this is the simplest model. Economists would frown upon this, and I can't make any sense of it. So to finish up the talk, so the history of this Earth system matters, and so what? So one very easy reason to care about it is that increasingly we're talking about climate tipping points. And it's very easy to think that, okay, I'm thinking about the ocean heat uptake. I'm just going to worry about the top 1,000 meters. I'm not going to worry about the deep ocean. But what I tried to show is that it's more complicated, and that the connection between those on longer timescales is actually essential. So there's quite a bit of fundamental understanding that's needed to be able to answer the tipping points. And so if you're in the physics department, a lot of us, if not all, have seen dynamical systems. We know about Lorentz cycles. We know about chaos. We know that the system is nonlinear and chaotic and hypersensitive to initial conditions. And so in the world that we're increasingly making complicated models for shorter timescales using AI, how do you constrain those models in the parameter space? So the way you do it is, one, by making sure that the model parameterizations or whatever physics or chemistry that you know is as good as you can and build it in, so they have a framework that you can actually work with. But But importantly, knowledge is still holding us back. So I was, like, if you think about atmospheric science, I would say it's more advanced of a field than oceanography, right? Or if you think about combustion and engineering, a field that I used to work in, is quite advanced. So advancement of knowledge is really incremental. But in this case, we're still asking basic questions in the ocean, whether things are going up or down. We don't still fully understand how waters go north in the Pacific Ocean. We know a lot of it happens, we don't fully understand how. So these are very first or zeroth order questions we don't understand. So it's a very young field, but it's becoming operational very quickly. So we are in the decades of ocean. One of the programs in that is the digital twins. I've been to a number of meetings. There are a very large number of very complicated models that are assimilating data, some global, some regional, for industry developed. All of them are for commercial reasons or geopolitics and so forth. And they all are very expensive. They all use AI increasingly and are run for a very short time. So how do you, like, if you think about the loops and climate bifurcations and all of that sensitivity, how do you get that history and actually build it in? So the solutions are constrained. Now, an example that this problem is known is coastal flooding. Coastal flooding as an industry is mostly a regional modeling, right? So they get the Met Ocean, the large scale climate model outputs, and then they use it as boundary condition and resolve and really worry about errors. But the error from the larger system doesn't propagate through their models. That's very difficult to solve, but I've been to a number of meetings of this. I'm involved with this, and I'm worried that very soon, the next 5 years to 10 years, we're going to be in a position that it's very hard to track of what we know and what we don't know and how constrained the solutions are. So one way that we can make sure that the solutions are constrained is data. And I showed a lot of things that use data that I didn't actually show you the connection, but they really rely on observational programs that are really key, really expensive, international. And even when it's absolutely clear that they're vital, it's not a given at all that they are going to survive. So SOCOM program funded by the NSF, measuring carbon related tracers in the ocean, really key. It just ran out of money. They barely extended it partially for 3 years, but it can very well go away. And I remember when I was a student here, when I started, Canada has a polar program, and it was the beginning of a conservative Stephen Harper's government, and that was shut down. So as a scientist, a lot of people really work really hard, and of course in this department quite a bit to sustain this. And so data is one way to constrain the models, but also it gives you an opportunity to see the mismatch between the data and the models. And that is where the knowledge gaps are, so you can actually go work out what you need to understand. So not punchlines, as I said. So I'm going to stop there, but before that, I just want to take the opportunity to thank the department for the time that I had here. It was the best, really one of the best phases of my life. And it went from the group that I worked with was fantastic. I now looking back in my 5 year of PhD, there was only once that I went to Dick's office and he couldn't talk. Anytime, I had to have a science point to make, not any nonsense. But if I had something interesting, he was always open to that. I can't do that now. And the courses I took, I learned GFT from Paul, Stephen Morris, Kent Ward. I just learned so much. The teaching faculty, David Harrison at the time, Jason Harlow, they really did a great job of preparing us. The teaching that we did later, like I still use that experience, the admin. So thanks a lot. I hope you enjoyed the talk. If you didn't, it's your fault. I'm your product, and I'm going to stop.